Is everyone doing okay? Are we good? So the class has made a quite sharp turn, right, from first lectures, totally different from, for example, today's lecture. All right, so we are almost done with the splines. There's one last thing we'll cover today, last but not least. It's a very important property. So it's a theorem that we will state and we'll explain and we will prove, okay? A theorem on natural cubic spline. So let's say specifically on the smoothness of natural cubic spline. I know we went through a couple of proofs in this class. Some of them are really long. Some took almost a whole class. Those took many, many pages of blackboard work. Those you can understand, appreciate, that's good. I will not test you with those proofs. But this proof that we're going through today, it's short and sweet. It's really nice. Okay? Every semester, every course, I pull out one or two really nice proofs and I say, I will test you on this in the exam, so make sure you understand and you can repeat this proof, right? Is that okay? And you will see it's really nice. Okay, I hope you agree with me in the end. It's a nice, nice proof. Okay, so let's set up. What does the theorem say? So it's about natural cubic spline. So I have a function s, okay? Let's say is a natural cubic spline okay, interpolating, that interpolating, let's say a function, the function f, okay, well, I need to fuss because I have to differentiate it twice. So it has to be twice differentiable. Let's say f is in C2. It's easier, it's shorthand. So twice differentiable, continuous differentiable function. And then at knots. Okay, so let's choose these knots on the interval from a to b. So a would be my t0, and then I have sorted t1, t2, all the way to tn, and that is the b. So you have an interval from a to b, and then the first knot is on a, and the last knot is on b. Okay? And then the following holds. If I integrate from a to b of my spline function, second derivative square is less than equal to the integral, the same integral, but for f. Okay? So f is a generic function, and s is the cubic spline. Okay. So I could even say this holds for all function f in C2. There's no specific constraint on the f except the spline interpolates it. Okay. So what is the meaning of this theorem? How is it related to smoothness? Why is it called Smoothness Theorem for cubic spline? So let's take a look at what we are integrating here. So what does it mean? So the theorem says that if you measure this quantity, that is the second derivative of the function square integrating from a to b, if that's the thing you want to minimize, then natural cubic spline is the thing that minimizes it, right? So this one, putting in the natural cubic spline, this quantity is the smallest by among all functions that you can put in. So f, any generic function f you put in here, you will get something bigger than or equal to. The best case, this equals to that. Is that clear? So what does it mean? Double derivative of a function, square, and then integrate. What is the meaning of this quantity to a function defined on the interval from a to b? Anybody, have we run into something like this in calculus? I think we have. So what is the meaning of first derivative? Is the slope. So look at the graph. It's how the graph goes up and down, right? So what is the meaning of the second derivative? Is the change in the slope, is it? So if a function has a big second derivative at some point, how would the graph look like? It would bend sharply, isn't it? Do we see that? Second derivative is the rate of change of the first derivative in x, right? So as you go in x, the first derivative changes sharply. So your curve bends sharply. So second derivative is related to something called curvature. We have heard of it? Curvature of a curve, how much it bends. And then, of course, you square it, you make the amount always positive, and you integrate over, and you get a positive amount. So for a curve that bends a lot, the curvature is going to be large, and that integral is going to be large. And for a curve that bends less, it will be small. So what the theorem says is that, so the meaning of it is that cubic spline has smallest curvature. Okay, so it does not do unnecessarily bending back and forth. So I actually checked out the word spline. Anyone check that out? Last time I was not able to say it. Do you know why this is called spline? Spline is actually a tool that graphic designer use. It's a metal strip, very flexible, and then you have a couple of control points, and you want your curve to go through these points, but you want it to go through smoothly without unnecessary bending force. So you fix this flexible metal strip at those points and let the what is it called, the tension fit it in. That's the tool called spline. That's the name. Right, so it basically does very much what this natural cubic spline does, right? Smallest curvature. Okay, so and to the human eyes, if a function has small curvature, of course it looks smoother. Okay, so if that's your goal, then cubic spline is your choice, and that's why we never needed to go to piecewise polynomial splines for degree higher than 3. There's no need. We don't even touch the quadratic spline, okay? Because this is the most desirable one, in a sense. Okay, of course, if you prove it. Okay, so let's do that. Let's try to prove it. So I need some help. I define a function. Let's call it g, just to be the difference between f and s. Okay. It's kind of the arrow, right? And what do I know? What properties does it have, this function? If I evaluate g at all the knots, what do I get? So how is the function f related to s at the knots?
They're equal.
They're equal, so the difference is 0, right? We agree? And that happens to all the knots, for all i's. Okay, I will not write I from 0, 1 to n, just for i's, so it's clear. Okay. And okay, now let's do some manipulation, because in the end I need to figure out the integral of the square of the double derivative. So let me write f in terms of the other. fx equals to gx plus s of x. That's obvious, and the dependence on x is obvious, and then I'll throw it away. I will not write x anymore. So f double prime will equal to g double prime plus s double prime. Is that right? Differentiation is a linear operator. You can differentiate each term and add up afterwards. It's the same. Okay. And then I want to understand the square of this second derivative. I'm just constructing. So I will get g double prime plus s double prime square. I'm going to open this up. So g double prime square plus s double prime square plus 2 times G double prime S double prime. Is that okay? I haven't done anything yet so far. It's just algebraically manipulating a little bit. Okay, now I know the double prime square, I will have to integrate from A to B because that's the quantity I want to study. So what I'm going to do now is I'll integrate on both sides from A to B. Okay? So what do I have? Integrate from A to B, F double prime square dx equals to integrate from A to B. I'll integrate each term and the last one, I can take the 2 out. Okay. Is that okay? Still haven't done anything yet other than integrated each term. So, okay, let's look at this. This is on the right hand side over here, and then this guy here is on the left hand side. My goal is to show that this is bigger than that, right? Let's look at the 2 other terms on the right hand side. What can I say about this term without knowing what G is? Can this term be negative? No, because you're integrating something that's non-negative, right? So this term here is bigger than or equal to 0. Agree? Right? So now I come to the observation, well, kind of observation. Now, if somehow by magic I can show the last term equals to 0, I'm done. Do you see? If this is 0, then I have something positive equals to something non-negative plus that, then this must be less than that. And that's what we want to prove. Agree? Let's make that claim. Now I tell you, I claim this is 0. Claim the integral from A to B of G double prime of x S double prime of x dx equals to 0. So if the claim holds, then we know we're done. If it holds, we're done. We prove the theorem. Okay? So now we need to prove this claim. So how can we prove this very strange claim? We say that integral has to be 0. Okay, so there are all these derivatives in there. So what we will be doing is something called integration by parts. Okay, so let me set up what will be the integration by parts that we will be using. So I will be using the following. Use okay, since would I go long? Yeah, use this. So S double derivative times G prime equals to S triple derivative G prime plus S double derivative G double derivative. By this integration by parts is just the product rule, isn't it? So the integral of this one, which we have here, equals to the boundary value of this term minus the integral of that term. Is that right? Okay, so we will have the following. Integral from A to B, G double prime, S double prime dx will equal to S double prime x, G prime of x, evaluated at A to B, minus integral from A to B of this term as triple prime of x, G prime of x dx. So remember, we want to show this is 0, okay? Let's try find some zeros. What can we say about this first term that's evaluated at A and B? Oh, I lost, yeah, it's fine, I'm right. Right?
Well, if A and B are both t values and G is 0 for any value of ti, then evaluate at A and B, obviously equals 0.
But this is G prime.
Well, I mean, if g is 0, then the derivative of 0, would that also be 0? Or not necessarily?
No. What's special about A and B? They are the end point of my knots. Is that right? And I am talking about natural cubic spline. What's so special about natural cubic spline? Remember, we add 2 additional conditions to make up the number of equations equal to the number of unknown? What was that? This guy, is that right? S double prime equals to 0 at A and B, right? Remember? So this thing equals to 0 because S double prime at A equals to 0 and S double prime at B equals to 0. That's the condition for the natural cubic spline. Okay? Okay, so the first term is 0. Then we have to show the last term is 0, is it? So how can we show the last term is 0? Let's look at it. So what do we know? We know S of x is piecewise cubic polynomial. So on the interval from ti to ti plus 1, it's a cubic polynomial. And here we are integrating S triple derivative. So what can we say about S triple derivative? On the interval from ti to ti plus 1, each little subinterval, what is the third derivative of a cubic polynomial?
It's going to be a constant.
It's a constant. Do we all see that? This, in the end, is a piecewise constant function. Do we see? So piecewise constant. Okay, so let's denote it by something. So let's say S triple prime of x equals to ci for x on the interval from ti to ti plus 1. Is that okay? Okay, let's make it left continuous. Is that okay? All right. Okay, then let's look at this integral. So integral from a to b, s triple derivative of x, g prime of x dx. Okay, so what I do is I break this integral from a to b into summation I from 0 to n minus 1 over each interval ti to ti plus 1. Okay, I break it into, you can integrate each subinterval, then add them up at the end. And then on each subinterval, what is S triple derivative? It's a constant. It would just be a ci, is that right? Times g prime of x dx. So ci is just a constant. It doesn't have anything to do with the integrating variable x. So I can move it outside the integral sign. Can I? You can do that. Okay, now what do you have? You are integrating a derivative over an interval. What does that give me? Yes, the fundamental theory of calculus tells me this equals to g at ti plus 1 minus g at ti. Okay, I say I'm done. Do you agree? What do I have here? Matt was trying to tell us, don't forget g equals to 0 at all ti's, right? 0, 0, bunch of 0 add up, it's 0. And we're done. Is it nice, the proof? Okay, allow me to indulge myself and say a few things that might sound very strange. So what does it mean? The claim, your claim. So you have this function. You have a cubic spline, and which interpolates a function f, and then g is the arrow, right? So in the end, what do we show? We show that the arrow second derivative times the spline second derivative and integrate from a to b is 0. So if you're familiar with the concept of inner product, this is an inner product. You multiply two functions and integrate from a to b is an inner product. Okay. So if this is inner product, what it says is that the arrow, the cubic spline, the distance between cubic spline and the function is orthogonal to the cubic spline measured in this inner product. Okay, so what does it mean? Meaning it's a projection of a function f down to another space in a perpendicular way, and the distance is vertical to the space of all cubic splines. Okay. Sorry, I said I'm indulging myself, but it's okay. So that might help you remember what you have to claim here, right? It's some inner product equal to 0, then the two things are perpendicular, all right? Okay, so any questions? We're done with this chapter. We move on now. Any questions on this proof? Is it okay? It's not a bad proof, isn't it? It's very basic manipulation, right? Integration by parts, and that's all. All right, move on. Next chapter is a chapter closely related still to polynomial interpolation. So this is now we're going to integrate. So numerical integration. This is also called a numerical calculus, because calculus is about integrals. So numerical integration. So the real application, the most important application of numerical integration actually lies in something that will come much later in solving differential equations using the weak form, the variational form. Later on, if you shall take graduate course on finite element, for example, this is a key component in it. Okay, but right now we'll just take it as a way to approximate the integral. Okay, so keep in mind this has huge applications. So the problem is the following. I have a function given on some interval from a to b, and I want to find the integral. So I call it I of f. So integral of this function f from a to b of fx dx. Okay? So this fx might be nasty, that it's very hard to work out the antiderivatives. We know from calculus finding antiderivatives is not always easy, right? Differentiating is somehow a bit easier. Okay? So we will not compute this exact. We will find an approximation to it by following the ideas. So here are the main ideas. So I'm sure everybody remembers the definition of the integral is exactly defined through something called Riemann sum, right? You cut the interval into many little pieces, and on each skinny strip, on a very small interval, you approximate the function by a piecewise constant, and then you add them up, and that's the Riemann sum, right? And we'll do borrow that idea, but we extend it. Okay, so what we do will be step 1. I cut up AB into subintervals. Okay, so what should I call this? Interval is usually is I. So you have an index. You cut it up like that. Okay. And then on each subinterval, on each I, what do? We approximate f by some polynomial pi. Let's put I under. I think later on I use it under. Pi is some polynomial. What degree? Well, to be determined. Depends on the problem. Depends on what you want. And then integrate pi on II. as the approximation. Okay. Is it clear? It's a very simple idea, isn't it? So if you use a lower degree polynomial on each subinterval, you end up with a simpler method and probably not so higher accuracy. And if you throw in a higher polynomial, the method gets more complicated and you get higher accuracy. Okay, it's always that case. So let's look at the simplest case. Well, the simplest case is the Riemann sum piecewise constant. That's really too rough. It's of no use numerically. So we go in one step higher, called Trapezoid Rule. I'm sure you have heard of it. Have we? Trapezoid Rule, we have heard it, right? Okay, so let's set up the grid. We need some notation. Okay, so you have an interval. Cut this interval A, B into, let's say, n pieces and subintervals. Okay, so like this. So x0 equals to A, and then I have in between, it's sorted, so xi is less than xi plus 1, and the last one, xn, equals to B. All right? Okay, and then now we just need to look at an interval. On this interval, xi plus 1, what do? We approximate f by a polynomial, a linear polynomial. Okay, let's call it pi on this interval such that it interpolates. So pi at xi equals to f at xi, and pi at xi plus 1 equals to f at xi plus 1. It almost takes longer for me to write than just draw a picture and you see what it's doing. Formulas actually are heavier here, so let's draw a picture and see. It's a bit easier. Okay, so this is x. I'm drawing a function f. Say, let's say f looks something like that. Okay, and let's put an interval. Draw a little bit big so you can see. So xi plus 1. Is that okay? And then what it does is, on this interval, I'm going to approximate this function here. Right now, it's something curved like that, by a linear polynomial that interpolates these 2 points, meaning I'm just connecting these 2 points with a straight line. Then my function is approximated by piecewise polygonal lines, right? And the integral will be the area below, right? So I will just integrate my polynomial instead, meaning I will use the area of this trapezoid for the integral of f on that interval. Is that clear? That's why the name, the trapezoid rule. Okay, so the integral from xi to xi plus 1 of f x dx is approximated by the integral from xi plus 1 of my p on the I x dx. I really don't care about writing out the exact expression for this pi and work out, because I see it's the area of this trapezoid. Do we know how to find the area of the trapezoid? Is the half of the top plus the base. The top is f at xi, the base is f at xi plus 1, right? And multiply by the height. The height of my trapezoid is the length of the interval. Do we see? Okay, so xi plus 1 minus xi. Is that okay? That's the area of the trapezoid. Okay, so, and then you just add them all up. You do it for each little subinterval and you add them up, like the Riemann sum. Okay? Then we have the following. integral from a to b of fx dx, and you cut it up into I from 0 to n minus 1 xi plus 1 of fx dx, right? And then you approximate this with the trapezoid, with the polynomial. Okay, I'm just being painful and write it all out. Okay, so what does it give me? Well, this is a half of fxi plus fxi plus 1 times xi plus 1 minus xi. Okay, so this is the general formula, okay? Let me put a block around it. This is a general formula for any distribution of xi's. Okay, and in practice, it does happen that you put xi's in an uneven way to achieve certain accuracy. Okay, but a simpler formula exists if you put in uniform grid. So let's look at that. Uniform grid, it's much simpler and it's really desirable. So what does it mean is that you would cut your subinterval in a uniform way, that is, each subinterval have the same length, right? We talked about uniform grid. So h now denotes the length of all subintervals. It will equal to the total length of the interval divided by number of subintervals, right? And then you know xi plus 1 minus xi for any I equals to h, right? That's the uniform grid. So, which means in the formula here, this guy equals to h. Oh no, I lost the summation sign. Nobody saw that. Nobody remind me. I lost the summation sign. I from 0 to n minus 1. Okay, you have to sum it over. Otherwise it's one term, right? Okay, back to uniform grid. This guy will just equal to this h here, which means you can take it out and put it in the front. It has nothing to do with the index, right? So let me write this out in a bigger way. So integral from a to b of fx, can I use this notation? I of f is approximated by, let's take out the h. And the 2 is also, and the half is not depending. Summation I from 0 and minus 1 f xi plus f xi plus 1. Is that right? Okay, I'm going to do something. Motivation, I will explain very soon. I want to see exactly what is in this summation sign if I write it out. Is that okay? If I equals to 0, what do I have is f at x0 plus f at x1. Okay, this is I equals to 0. And then when I equals to 1, I get f at x1 plus f x2. Agree? This is I equals to 1. Sorry. Not so fast. And then comes I equals to 2, fx2 plus fx3. This is I equals to 2. Okay, so on so forth. Let me write out the second last term, that is n minus 2 fxn minus 1. Okay, this is really long. So that's I equals to n minus 2, and then you have one more term, which is the last one, xn minus 1 plus fxn. And this is I equals to n minus 1. Okay, so the reason I write it out, well, several reasons. So we are going to code this algorithm in a computer. So you have to be aware what is computationally costly and what operation doesn't matter, you can afford to do, right? So we talked about first week of class, we talked about for many of these fancy functions, say even the exponential function, or sine or cosine, if that's your f of x, the computation to evaluate your f is going to be much more expensive than any of these adding. Remember? We talked about it. So when you are designing an algorithm, you want to be aware of saving your CPU time. Say here, f at x1, f at x1 appear twice. So if you stick to this formula and simply write a for loop for this, you ended up evaluating f at x1 twice. Wastes a lot of time. You see? You could just combine them and multiply this by 2 to save. All right? So that's why we listed out, and just to see these multiple ones. Okay, and then I see that actually I could join these together and multiply by 2, and then these two, you can just multiply it by 2, and so on and so forth, and then you see all the inner knots, the inner points, the f evaluated at there can be multiplied by 2. The only one that doesn't do it is at the 2 boundary, this one and this one, right? Do we see? Okay, so consider the half there, so this will give me h times, I'll put in the half here, so a half of f x0 plus f xn. Okay, I take the 2 endpoints and take care of them first, and then what do I have afterwards? All the inner knots, they are multiplied by 2 and divided by 2, and it's gone, the constant. So f at xi, I from 1 to n minus 1. Okay, so if you're reading this as a code, you know this code, this line here is much more efficient than this line, right, computationally speaking. Okay, so I want to introduce a notation. So this here is a trapezoid approximation to the trapezoid approximation to the function f using the grid size h. Okay, so that's the notation. Later on we'll be just writing like that. Okay. Is that okay? So what I want to do next will be talking about coding. In the lecture notes there is a very silly example with 11 data given, data containing like 8 significant digits. No, you can read it. I'm not going to write this on the board, right? Just how to do it with trapezoid rule. Okay, I'm not going to do that. So what I will do now will be talking about how do I code this in MATLAB. Okay, a couple of ways of doing it. What's most efficient? Okay, so we would want to code this piece here. We want to code this piece. So let's say a function is given. What do you want to be? Fx equals to some function. How about e to the x plus sine x plus x squared, just a random function, right? So you will need to define this function first, isn't it, in MATLAB? Have to define this function, so let me just write code on the board. This is MATLAB syntax. So I want to define function, returning value. Let's just call this function f, and it sends z and x. And this shall be saved in a file called f.m, right? So you need the file named f.m. It will contain the following, just 3 lines. Okay, so the v, now I want you to define it such that x can be sending as a vector and it returns v as a vector. Okay, so you will write exp of x, exponential of x, right, plus sine of x. Those two are predefined in MATLAB. They can handle vector inputs, and plus x squared. So the normal expression to do square would be this upper thingy and 2. But if you do that, that can only handle a scalar number x. And here the x is a vector. So what do I have to do? I have to use this dot. Okay? Then you can handle a vector. And that's it. And. Okay, so this is, you need to call this function, and then let's say I have some data that's already given. We already know what is A, what is B, and what else do we need to know? And let's say these are given. How can I write a script, okay, in MATLAB that will compute this? Okay, so I'll need to first find what is my h. It would be B minus A over N. Is that right? I need h. Okay, and then probably you want to set your x vector. You can use the line space, or you can use this A, H, B. That gives you a vector of length n plus 1. Is that okay? And then the value will be returned in this variable called t. I'll store the integral in the t. So look here. The first step, the t will be computed as the value in this bracket, okay? So I will send this to t first, and then I do a for loop to sum these up. Is that clear? Okay, so this will be f at A plus f at B over 2. That's outside, right? And then I need a for loop for I is 1, 1, all the way to, no, it's not 1, 1 in MATLAB. I have to start from 2, 1. You have to increase the index by 1 because it doesn't start from 0, right? So 2, 1, and all the way end at n. Now hopefully I'm correct. Okay? And then what do? You take t and you modify the value by t plus one of those guys, f at x at I. Is that clear? Okay, and okay, put a semicolon. You don't want all that output. Now what will be the t value when this finishes? It will be the value of in this bracket. Is that right? But then in the end you have to remember multiply it by nh. Is that okay? Can we write a code like that? I bet we can, right? Okay, I want to tell you something more. Now, this would be a code you would write if you are dealing with just a regular programming language. But you are dealing with MATLAB now. MATLAB has tons of predefined functions, specially designed for vectors and matrices. Okay, I want to say that this summation here, we chose to do a for loop. We don't have to. A for loop is slow. You could change this into, you can call a thing called sum. It's a function in MATLAB. It will add up all the elements in a vector and return the sum. Okay, calling that will be much faster. So an even shorter one, shorter in terms of shorter code and shorter computational time, would be the following. You still have to do the first two steps. So h, you have to initialize b minus a over n, and you have to set up your x vector. Now I'm going to set it in a tricky way because I know I'm going to call the sum here, so I will set it up as only the inner points. Okay, so this is actually the x1, a plus h, and it ends at b minus h. Okay, so you can put a comment. These are all the inner points, inner knots, meaning what this summation is doing. Okay, so once you have that, you can write it in one line. So t, what would that equal to? Well, you can just look at that and write it. It will be h times, in bracket, f a, okay, another bracket, plus f b, bracket, divided by 2, plus what do I do is the sum of f at all these x that I prepared here, the inner x, 1, 2, yeah, and 3. This will correspond to that one. And that's it. Is that right? This thing just does all that. Okay, so I don't know if it will be next time, or maybe next time I'll show you some computations